Welcome once again to this edition of the virtual seminar on precision physics and fundamental symmetries. I'm delighted to introduce today's speaker, Lindley Winslow. Lindley's an associate professor of physics at MIT, where she's been based since 2015. She received her bachelor's in physics and astronomy in 2001 and a PhD in physics in 2008, both from the University of California in Berkeley. She did a postdoctoral fellowship at MIT and was appointed an assistant professor at the University of California in Los Angeles, before then moving to become an assistant and associate professor at MIT in 2015. She's won numerous awards, including the L'Oreal Prize for Women in Science Fellowship, the Michelson Postdoctoral Prize Lectureship, the MIT School of Science Infinite Kilometer Award, the Breakthrough Prize in Fundamental Physics, which is part of the CamLand collaboration. And in 2021, she was elected a fellow of the American Physical Society. She's also got the distinction, which I really liked, of being one of the scientific consultants to the 2016 Ghostbusters movie, making sure that all the labs and the equations on the blackboard were completely authentic. She's part of the Core and CamLand Zen collaborations to explore neutrino-ness double beta decay, and she's active in low mass Axion searches, which is one of the topics we're going to hear about today. She's one of the PIs of the merged ABRACADABRA DMRadio experiment, and her talk today is on the search for Axion dark matter, ABRACADABRA 10 centimeters, and the DMRadio program. And with that, the floor is yours. Thank you very much, Lindley.
Thank you, Jack. And so I'm so excited to be here today. So as you heard, my group works on two things. We look for Axion dark matter and neutrinos double beta decay. And these topics are actually really great for this seminar series because they really are going after fundamental symmetries and these really big questions of what is dark matter and why is there more matter than antimatter, and what is that physics? What are the symmetries that are creating the universe that we see? So we are, I do consider myself a nuclear particle physicist depending on the day of the week. And of course, we're working within this, this greater theory of the standard model. And we know it's not complete, but we're really having a hard time of finding what's wrong with it. And in my view, what we really need to be doing is looking for new physics at the gut scale, because we know that something has to happen even within the standard model at this energy scale. And so, of course, this is the scale at which you have the unification of the strong and the electroweak forces. And so what unites these two topics that I'm really interested in is this new physics at the gut scale. And so on the right, you see sort of a classic seesaw mechanism, which explains why the neutrinos are so light. You include a heavy Majorana neutrino, and you naturally get this seesaw that sends the neutrinos that we know and love to the very light masses. And so if you look on the left, you see the mechanism for producing Axion dark matter, the Paget-Quinn mechanism. And what you find with that is that the mass of the Axion is inversely proportional to the scale of the Axion that you're creating. And so you see this nice coupling of sort of a nano EV Axion corresponding to new physics at the gut scale. So that's my argument as to why I work on these two topics, not just because the detector technology is cool, but that's true too. And that's where my focus is, on nano EV Axions and the search for neutrino-less double beta decay. But today we're going to focus on Axion dark matter. So Axions are different than the dark matter that you probably hear a lot about. And so what we've really focused on for the last, 3 to 4 decades is these heavy dark matter models, these WIMP dark matter models, where you're sort of swimming through a sea of billiard balls like you see on the left. On the right, I've been trying to draw, light Axion dark matter, but the Axion is actually so light that you have to stop thinking of it as particles and really start thinking of fields of wave-like dark matter. And so it does take a little time to kind of move your particle physics brain from these billiard ball, like true particle interactions to Axion dark matter. And just to give you an idea of the scales that we're talking about, we can talk about the de Broglie wavelength and the occupancy number of these two theories. And so if you're talking about a nano EV Axion, the de Broglie wavelength is 10,000 kilometers with an occupancy number of 10 to the 44. So you can really see that this is really a wave. versus a WIMP dark, sort of a canonical WIMP at 100 GeV. The de Broglie wavelength is 10 to the minus 16 kilometers with occupancy numbers as 10 to the minus 36. So these are definitely particles. And I like this slide just because I think it really emphasizes this point of how you need to think about axions. You're not building sort of classic particle physics experiments. So why axions? Well, this is a story, and so this is good for this group, of a fundamental symmetry. So of course, charge parity describes this mirror-like symmetry, and the violation of CP leads to particles and antiparticles behaving differently. This, of course, is the focus now of the whole neutrino oscillation program, and seeing that in the neutrino sector. We desperately want to observe more CP violation, but what's odd is we don't see this in the strong interaction. The strong interaction really seems to conserve CP. And so some details, what's going on here? So if you write down the Lagrangian for the strong force, you end up with this term on the right where you have these two gluon field strength tensors and this constant theta bar. This term of the strong Lagrangian gives rise to an electric dipole moment of the neutron. And so that value will be 3.6 times 10 to the minus 16 times this constant theta bar. So if you observe an electric dipole moment of the neutron, you see CP violation in the strong interaction. The problem is that we're really not seeing a neutron electric dipole moment. And I like this sort of cartoon from Brad Filippone at Caltech of, I'm sure this audience thinks about EDMs a lot, but if you think, if you don't, like you can think of a classic electric dipole, think of the neutron in the same way and kind of do some hand wavy order of magnitude math, and you expect you know, an electric dipole moment of the neutron kind of on the order of 10 to the minus 14 e centimeters. But experiment now is measuring at 3 times 10 to the minus 26 e centimeters. So we have a big difference. And here's sort of the current values. You see that beautiful progression of improvement on the neutron electric dipole moment. But we really are sitting here at 2.9 times 10 to the minus 26, which corresponds to a theta bar of 10 to the minus 10. So as particle and nuclear physicists, a constant at that level of 10 to the minus 10 might as well be 0. And so it really is implying that there is no CP violation in the strong interaction. And so now we need to explain why there is no strong CP violation. And so this brings us to the Paget-Quinn mechanism, which induces this new axion field, which dynamically sends theta bar to 0. You see the Lagrangian on the left, phi A over FA, the symmetry breaking scale that produces this axion field, and dynamically sends that part of the Lagrangian to 0. It does result in a new particle, the so-called axion, and the mass of this new particle will be inversely proportional to the symmetry breaking scale of this new U1 PQ symmetry that is introduced to the standard model. So yay, a new particle that we can go look for. So at first, they put the axion kind of up at the weak scale, and that was quickly ruled out in the early 80s. And so now we're left with these two broad categories of QCD axion models. And they are the KSVZ axion, which introduces heavy quarks in addition to this PQ scalar, the axion, and the DFSZ axion, which introduces additional Higgs fields as well as this PQ scalar. And so these are the two QCD axion models. These are the axions that can actually solve the strong CP problem and explain why the strong interaction does not violate CP. So yes, these are QCD axions. It turns out that a lot of higher order theories produce axion-like particles, and that they can happen at a wider range of parameter space. And I have to admit, within the axion community, we get a little lazy and we combine together QCD axions and the axion-like particles, the ALPS, and just call them all axions. And I'm going to be guilty of that in this talk too. So when I say axions, I probably mean ALPS and the QCD axion, unless I'm really like focusing on whether we've like searched for axions all the way down to DFSC. So that brings us now to the next question of, so we produce these axions and they're being produced to solve the strong CP problem. But it turns out that you have a nice light particle. They could also be dark matter. Pardon me. So how does this work? And so the classic question to ask is, how does something so light still do its job as cold dark matter? And so this is the part of the talk that I'm still working on. A good cartoon explanation. So tell me how you like it, and we'll keep working on it for the next time I come and talk. So the mechanism where you generate axion dark matter is called the misalignment mechanism. And so this is an athermal process. And that's the key here, is that axion dark matter has never been in thermal equilibrium, and therefore is sort of avoids all of the constraints from a thermal evolution like that for the WIMP dark model, for the WIMP miracle. And that's the key word there, is that athermal process. So how does this actually work? And so I'm following here this wonderful, very complete summary by David Marsh. And so the key is that you have two scales. You have the symmetry breaking scale, that F of A, and the QCD scale, where the Goldstone boson gets its mass. And so you write down a potential, you have this QCD scale, lambda of A. And then you expand this cosine-based potential, do Taylor expansion, and you find out that the mass of the axion is equal to the scale of QCD, where it gets its mass, divided by F of A, the scale at which you broke the PQ symmetry. And this is actually very reminiscent of the seesaw model that we saw, that I explained right at the beginning for neutrinos, in that you have this very high scale of some sort of symmetry breaking, F's of A, and then you have this much lower energy scale, the scale of QCD. And so you naturally end up with these very light particles. And so that's sort of a very nice sort of natural explanation why you end up with light axion dark matter candidates, and also producing them athermally. So now the job is to combine this particle physics with cosmology, and you have these nice plots like that. So the field equation quite literally is that of a harmonic oscillator. It starts out highly damped, and this scenario is all dependent on the initial conditions of the symmetry breaking and the scale at which the particle gets its mass. So you have for a while that you have this underdamped oscillator, and then as the universe expands, you'll hit a point where you become the field is able to oscillate, and then it relaxes down to the potential minimum. And so the misalignment refers to this relaxation down to the potential minimum. And because we are now having this underdamped field, you have this oscillation beginning. And at this point, the experimentalists move over from talking about a field as phi to the axion field as A of t, which gets confusing with the scale factor of the universe, but that you have this oscillating axion field, A of t equals A naught times sine MAT. So it'll be oscillating with a frequency corresponding to the mass of the axion. And 1/2 MA squared A naught squared gives you your rho dark matter. There's a lot of details here, but that's the general idea of how this misalignment mechanism works. And so then the key question is, how do you relate this to the dark matter density? And so you get this nice equation that you see here, omega A, omega axion dark matter is proportional to, inversely proportional to the mass of the axion, to basically the power 1 times theta bar squared. And so if you look at this and ask, why have we really focused on the micro EV scale up to now? Well, and that's the current bounds, just FYI. Well, you focus on the micro EV scale because that's the scale of mass of the axion where theta bar is equal to 1. And so that's very natural. And we like things where we just put in 1. And so a lot of focus has been on this micro EV scale. But it doesn't have to be at a micro EV. And so then the question is, given all of your possible axion masses, what is the best guess for the axion mass? So here is the full range of axion mass from 10 to the minus 22, where the wavelength of the wave-like dark matter is the same scale as a galaxy. Turns out your wavelength has to be shorter than the scale of a galaxy to work as dark matter, all the way up to the higher end at 10 to the minus 2 EV. And so you have two different scenarios. You have the scenario post-inflation for the PQ phase transition, which really sort of forces you to be in this sort of micro EV regime. And you have the scenario where the symmetry breaking for the PQ symmetry happens before inflation. And of course, inflation gives you a lot more wiggle room as to what the physics before inflation was. And so you end up with this much broader range of axion dark matter models. So there are other bounds from the angular momentum of black holes to stellar cooling, but this is the general sort of big picture. And I've of course taken this from the particle data group's Axion review. Excellent. So we do have a lot of parameter space to search over. So how do you detect axions? So when you add axions to the standard model, you add 4 terms that can be used for detecting axions. You have a coupling to photons. You have a coupling to nucleon EDMs, a coupling to the axial nuclear moment, and a coupling to the axial electron moment. The last 3 require a little bit more knowledge of your nuclear physics. And the first one, the coupling to the photons, is the cleanest. And so that's where a lot of the focus has been, because we're really good at measuring photons over their full wavelength. And so that's also the focus of my group. So if you're talking about the coupling to photons, you're talking about modifying Maxwell's equations. And so here are the axion modified Maxwell's equations. Oftentimes we neglect the gradient term already. This is going to be a small correction. And then what you're left with is the correction to Ampere's law, the last one. And so you end up with 3 different regimes for axion photon searches. You end up with this regime called the cavity regime, where the Compton wavelength of your axion is proportional to the size of your experiment. And so you're doing lots of cavity QED calculations. You have this regime where the wavelength of your axion is much, much larger than your experiment. And so this is the quasi-static approximation, and the type of experiment that you're going to be doing looks like a lumped element circuit. And in this regime, what's really neat is you have effective currents. And this is very, very basic electricity of magnetism. Quite literally, you can use the right-hand rule as you see to understand your experiment. The last regime is the so-called radiation regime, where the Compton wavelength of your experiment is much, much less than the size of your experiment. And this is the third and the heaviest mass regime for this type of search. Excellent. So the lumped element parameter space. This is where I'm interested in, because it's in this parameter space where the Compton wavelength of your axion is much, much larger than the size of your experiment, where you can go after nano EV axions, the so-called gut scale axions. And as I tried to convince you in the beginning of the talk, my interest really is this new physics at the gut scale. And so that's where we're going to be looking, and how do we actually do it? And so there's the point. MA proportional 10 to the minus 19, sending it to the gut scale at 10 to the 16 GeV over FA. So how do we do this? This would be ABRACADABRA. This actually stands for something, and I have to credit my collaborator with Jesse Thaler for coming up with this acronym. And so what it stands for is a broadband/resonant approach to cosmic axion detection with an amplifying B field ring apparatus. Yes, that is quite the acronym, but it also tells you exactly what we're doing. We're looking for axion dark matter with a B field ring apparatus, and we have 2 choices for actually how we do the readout. And so let me walk you through this. So looking for this Axion dark matter, and we're going to focus on this sort of pre-inflation scenario. So I left in some old slides, sorry about that. So here is the cartoon version of the abracadabra experiment. So we have a toroidal magnet. We have the B field running around the toroid, as you see here. You have the axion, which will couple to this B field through that modified Ampere's law and create an effective current. The beauty of this effective current is that it can generate a real magnetic field up through the center of the toroid, where classically there should be no magnetic field. And so you can do the right-hand rule and check this drawing. You put your thumb in the direction of the effective current that's oscillating with a frequency corresponding to the mass of the axion, and you get this field up through the center of your toroid. As an experimentalist, this is very attractive because it's effectively a low background experiment. You've created it so that you're measuring zero unless you see an axion. So what does the signal actually look like? Axion signals are really nice. They're very, very narrow. So the frequency is equal to the mass of the axion, and the width of it is about 1 part per million. And so if you're like looking across your readout in frequency space, you'll see, you know, a forest of lines corresponding to the inherent noise in your system, and then a spike will rise up through on top of the noise for your axion. There is a detail, which there is some intrinsic width to this signal due to the velocity dispersion of axions in the halo. So you're actually even given a little bit more detail on that signal than what I've shown here. So what did we need to get started building Abracadabra? So we needed a magnet. And so this was provided by an NSF Eager Award. We needed a dilution refrigerator, which I already had in the lab. We needed a squid current sensor. And so we had to go buy one of those. And we needed to do something about vibration isolation and some warm and cold shielding. So does this experiment work? Were we able to put these pieces together and actually get a physics result? And I guess you know the answer to that since I'm here today. And so here is what we built. And so we needed to build a toroidal magnet. And so it starts with these very pretty Delrin pieces that you see here. You sandwich them together to form the mold that you will wind the magnet around. Our magnet company then wound it and sort of packaged it in the epoxy that you see here with some copper cables for doing the thermalization. You have a ring in the center of the toroid for reading out the signal, and a ring running through the toroid for us to use as a calibration for the experiment. We can generate some fake axions. So Abracadabra 10 centimeter was installed for the first time in the fall of 2017. And there it is in my dilution refrigerator. It didn't work the first time. We had probably installed the pickup loop a little too close to the edge of the magnet. So we did some improvements to the geometry, and that was done in January of 2018. At that time, we also worked on the suspension of the system, some very simple vibration isolation. So the whole system is now suspended via a Kevlar string to the top of the fridge. And the Kevlar is used because it has very, very poor thermal conductivity. This is the world's simplest vibration isolation system. And so this is actually one of the focuses of future work. And so here's everything installed. You see the magnet in its superconducting shielding. You can kind of make out that Kevlar string from which the whole thing is suspended. And then the thermalization to the mixing chamber plate via some copper tape. The squids are up for this run at the 700 millikelvin stage. So speaking of the squids, here is the ABRA part of Abracadabra. When reading out this experiment, you have this pickup loop for picking up the Axion field. You can directly couple this into your squid current sensor, and this is the broadband readout, in that any frequency of signal coming through the pickup will directly go into your squid. It's very simple, easy to engineer. You just need to wire up the pickup loop. The second option is a resonant readout, where you couple the pickup loop to the squid via an LC circuit. What's beautiful about this is that you get a signal enhancement proportional to the Q value of your LC resonator. You know, getting something like 10 to the 6 enhancement would be very possible. The problem is that you now need to be able to scan in frequency, so tune the frequency of your LC resonator, and you have to design a cryogenic LC resonator. And so that was not within the budget of the first running of Abracadabra, but it's definitely at the heart of future work. And so for a full review of all of the issues of this technique, I point you to a paper by Saptarshi Chaudhuri and Ken Irwin that really goes into beautiful detail of exactly the engineering that needs to go into this resonant readout and scan strategy. But yes, for ABRA, we're going to go with the broadband readout and see what we see. And so, as I said, we have a 2-stage current sensor and amplifier. It's sitting at 700 millikelvin, and we are looking for a noise floor at 1.2 microphi-naught over root hertz. And we have to add additional filters to even limit the bandwidth further from 2 kilohertz and at 2 megahertz, just due to the noise in the system, not due to the readout. And so then the last upgrade that we did before doing our data taking was add magnetic mu metal shielding. The fun story about this is for a long time, MIT ran a small accelerator facility that was just decommissioned. And so quite literally, we went and harvested this mu metal off of the accelerator. And we went and got some more as needed. So the first results from Abracadabra came out in October 2018 and resulted in a PRL. There's also a long technical paper that was put out at the same time. And this is the data. And so, of course, we're looking for this oscillating Axion frequency. So the whole analysis is done in frequency space. Because we're doing a broadband search, you end up seeing the full frequency range at the same time. And that's kind of nice because it ends up looking like a little bit more like an energy spectrum that you would get from a particle physics experiment. So conceptually, the analysis maybe is a little bit easier, but we're definitely working in frequency space. So if I could focus your attention at low frequencies, you see this forest of lines. These are not axions. This is the induced signals due to the mechanical cooling of the fridge. And so that's really what's limiting our reach at low frequencies. At the highest frequencies, you start seeing kind of the limit of our EM shielding and some large noise sources getting in, hence why we had to add some filtering at high frequency and low frequency in order to run. What's beautiful, though, is in this mid-frequency band, we are basically at the squid noise floor for our device. And so this is a beautiful band to go and search for axions. And so I can point your attention to the blue line at the top labeled B of zooming in on a very particular frequency range and an example signal. And you see that it's a spike with a little bit of a shoulder to higher frequencies due to the velocity distribution of axions in the halo. And so that's what we're going to be looking for in this nice region where we are at the squid noise floor. So a key, and actually one of the experimental details that was hardest to get right is actually calibrating this experiment. So we have this calibration loop where we can inject Axion signals at a variety of frequencies, and then reproduce or calculate our gain. We can calculate our gain from sort of first principles, but what happened was that we found out that we were a factor of 6.5 low in gain relative to our theoretical calculation. And when you are doing this sort of readout, parasitic inductances just of wires running to each other can change the gain of your experiment. And so we had a lot of work to understand that. But the nice thing is, if you calibrate, as we did, you know what your system gain is. It's just kind of being able to understand the details of where you're losing gain. So then actually performing the search, we limited our search range from 75 kilohertz to 2 megahertz. This is that region where we had that we were basically at the squid noise floor. For each mass point, that's 8 million mass points, we calculate a likelihood function. And the discovery is based on a log likelihood ratio between the best fit and the null hypothesis. We set a 5 sigma discovery threshold, and this corresponds to a test statistic 56.1, accounting for the look elsewhere effect. And so we see some nice agreement between the observed versus expected distribution. And so using this method at each of those 8 million math points, we saw no 5 sigma excesses that we couldn't veto with magnet off data. That's the beauty, is you can turn off your magnet and any points that are still there obviously are not axions. And so 87 mass points of those 8 million were vetoed using the magnet off data. We then placed a 95% upper limit using this log likely ratio test. And that's what you see here. And what we were very proud of in our sort of first attempt is that we were able to come close to the solar axion experiment CAST, which of course ran at CERN on our first attempt here. And so here is sort of the full parameter space. On the x-axis, you have the axion mass versus GA gamma gamma, the coupling of the axion to photons. On the far right, you see the cavity experiment ADMX, sort of the longest running axion cavity experiment that's really focusing on that micro EV range. You see the broad limits coming from solar axions and CAST, and then the abracadabra limits. So this first sort of direct search for axion dark matter in the sub micro EV range. So then in the last few years, more recently, since 2019, we've been setting up for a third run. This was complicated by COVID and not getting access to the detector for debugging purposes after we started. And so what we did is we upgraded our calibration loop to a calibration signal. And this provides a stronger coupling to the axion field, a lower inductance to increase our gain, and then some cleaner wiring so that we better understand our parasitic inductances. We also moved our squids down to a colder stage, which will lower the squid noise floor. Unfortunately, with our better coupling, we also were better coupled to our environmental and vibrational noise. And so, so we ended up with a lot more understanding of our noise than I think we would have hoped for. And so then the run 3 data taking was 2 weeks in June of 2020. And I'm highlighting up there the lead graduate student, Chiara, who ran all the ComSol and did the upgrade and proved that we really understood the gain of the system, and our younger graduate student, our junior graduate student, Callie Roy Pappas, who did all of the calibrations for this run. And so this is the new data. And so in blue, you see our old results. We did improve our limits by a factor of 4 to 10. We moved below CAST for the first time ever in the sort of nano EV region. I would point you to the bottom of the green line. That is actually where the limits are. It's very hard to plot millions of mass points. But what you're seeing is that we are no longer limited by the squid flux. What we're really limited by now is our environmental noise. And so, how well we are reducing vibrations and how well we're shielding from external noise sources. And in the meantime, we also had other experiments joining in. And so you see a line from Shaft, and which actually very nicely proves the vibrational noise hypothesis, since they have a wet dilution refrigerator and aren't as plagued by the mechanical cooling. So that is the latest and greatest from ABRACADABRA. And so then the question becomes, what are we going to do next? And so we've really done what we can with our cute little toroidal magnet, and we really need a bigger magnet. We'll still need a dilution refrigerator, but probably a slightly bigger one. And we need to move to this resonant readout. And we're going to need to do a better job with our vibration isolation and some cold shielding. And so in the meantime, we have joined forces with our friends at Stanford and put together a very long-term program, the so-called DMRadio program, that will move us through these upgrades and through several different stages to really do a definitive search for QCD axions. And so the next one is DMRadio 50 liter, which is just a slightly larger version of ABRACADABRA. And will also be used as a test bed for quantum technology. We have DMRadio cubic meter, which is a DOE, which will be a DOE project, which currently is funded for a design study. And then my dream, which is DMRadio gut, the so-called ultimate QCD axion experiment in this regime, which will require quite a bit of R&D, both on the quantum sensor readout and the magnet technology. That's something like a CMS scale magnet being used for axion dark matter research. So the DMRadio cubic meter consortium is what you see here. So the lead is Kent Irwin, who is the PI at SLAC/Stanford. And I'm joined by Carl Van Bibber from UC Berkeley, Saptarshi Chaudhuri from Princeton, and Reiko Henning from UNC Chapel Hill, and Dale Lee from SLAC, who is our program manager, not our program manager, our technical coordinator. And so we are really excited that this is sort of ballistic now, and we will have sort of in US speak a CD1, CD2 style proposal in the next year. And so then to sort of wrap it up, I need to thank my greater group. The lead postdoc on this is now staff researcher, Dr. John Ouellette, who made everything work, the lead graduate student, Chiara Salemi, and the lead theory graduate student, Josh Foster, who did a lot of the work on the analysis, in addition to a great team that you see here. And so that's what I had to tell you about today on the ABRACADABRA front. And so I'd like to open it up for questions at this point.